Okay guys, so we'll discuss today a type of digital to analog converter, that is binary weighted resistor. First we will see its block diagram and then we will move on further with its working. Okay, so let's see its block diagram first. Follow me how to construct its diagram. First we have a line, then another line like this. This line is connected to ground and this line is connected to a voltage V reference. Okay, now from this line, okay guys, so we have constructed this at the moment. Now here a line in between these two lines and so on, and finally joining them, the final output goes to an op-amp whose positive terminal is connected to ground. Okay guys, so this is our block diagram for this binary weighted resistor. Now let's discuss some points. Now we can see many resistances in this block diagram. Okay, so let's say the first resistance here is 2 raised to power 0 and 0 into R, then 2 raised to power 1 times R, and so on. If we assume that we are dealing with n bits, so we will have n resistances now as it starts with 0, so the last resistance will be 2 raised to power n minus 1 R. This will be 2 raised to power n minus 2 times R. Okay guys, I hope this is clear. Now what are these? Why this line is connected to ground and this is connected to a voltage? These are nothing but bits, as the name suggests, binary. So this one, either this line is connected to the voltage or either it is connected to this ground terminal. Okay, so now let's name them. This is B0. Now again we are dealing with n bits. Alright, so this will be B n minus 1. Okay, now let's assume the current flowing from here is I0. Here it is I1 and so on till In minus 1. Alright, now the total current will be combined and will pass from here. Before moving further, we need to discuss the two properties that make this op-amp unique. First one is the input current of op-amp. Here input current of op-amp is equal to 0. That means all the current will flow from here and the voltage at this point Vx is 0. Okay guys, now let's move on further. Now we know by using the Ohm's law we have V is equal to I times R. Alright, now first of all we need to sum all these currents, that is the total current I is equal to I times I naught plus I1 plus and so on till In minus 1. Now we need to apply the Ohm's law. Now if V is equal to IR, then V upon R is equal to I. Just one thing extra here. We need to multiply this thing by bit number. Now why by bit number? Because if it is connected to 0, then this whole current will be 0, and if it is connected to 1, then it will remain as it is. I hope this is clear to you guys. Now let's put the values here. Now first we have voltage V0 here and 0 here. So 0 minus V0, and the resistance across this voltage drop is RF. Okay, now for I0. Now for I0. I0 will be V, whatever we are taking, V reference upon 2 raised to power n minus 1 times R. Okay, so similarly I1 will be V reference upon 2 raised to power n minus 2 times R, and so on. In minus 1 is going to be V reference upon 2 raised to power 0 times R. Now we just need to put these values in this equation. Okay guys, let's do it. We are doing nothing, just putting the values. So here we have a thing. So now this becomes, just solving this equation, minus V0 upon RF is equal to, V reference is to be common and R as well, and we can write this as summation of Bi upon 2 raised to power n minus I minus 1. Now from where we got this Bi? I just told you we have to multiply it with this bit in order to check whether the current is 0 or it is as it is. So the first this one was B0, this is multiplied by B1, and this one is multiplied by Bn minus 1. So this is the final equation we get after solving this. If you want to verify, let's check it. Let's say I is equal to 0. For I equal to 0, it becomes minus V0 upon, let's check this one only, no need to check this. It becomes B0 upon 2 raised to power n minus 1. Now this matches with this one. That means we are correct. Okay guys, so I hope there is no problem in understanding this concept. If you have some doubts, you can write in the comment section. One last thing guys, before ending the video, I just want to tell you that this is the least significant bit and this one is the most significant bit. Why most significant bit? Because its current, when we talk about its current, and from here we can see B0 is divided with the highest resistance. So that means it will have very less effect. That is, its weight is very less. So we say LSB is V0, B0. Similarly, for Bn minus 1, we have less resistance compared to all of these other resistances. So we say its weight is highest. So it is most significant bit.